Okay, this is going to be number 8 from Friday's assignment on friction and forces. So here we have a student from 7, and remember that 7 is this one right here. Oops. So a student is pulling a box of books down the hallway, yada, 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 yada. The box has a mass of 35. Okay, so it's the similar idea for that one, except now they're going to be pulling the box up a ramp. So let's just start with what it looks like. So here we're going to have a ramp, and the box starts from rest at the bottom of the ramp. The incline itself is 12 degrees, and the angle it's being pulled at is 25 degrees. It says with respect to the incline. That's what that means. It means that it's 25 degrees with respect to the incline. And this is 185 newtons of force. And the mu sub k, the coefficient of kinetic friction, is 0.27. We already know that the mass was 35 kilograms. Not that it's going to matter. Remember that the mass will probably cancel out in this case. And it's asking for what is the acceleration up the ramp. Okay. So I'm just going to quickly draw some force vectors in here. We have mg going down, perpendicular to the surface plane is the normal force, and pointed down the ramp is the force parallel. And just, again, just to make this a little tidier, I'm going to swap the position of mg. I'll put mg over here. Okay. So this is sort of our force triangle, and of course we're going to have friction that's going to oppose this motion. So you're pulling it up the hill, up the ramp. That means that friction is going to point down. Okay, so those are our 4 force vectors, and we're trying to figure out the acceleration. So let's begin, shall we? Well, F net equals ma. Again, net means total. We're interested in all, since this object will accelerate up the ramp with some unknown acceleration, the only thing we're interested in are the forces that align up or down the ramp. And there's only 2. There is the frictional force and the there's 3. There's the frictional force pointing down, there's a parallel force pointing down, and then there is the one which I neglected to draw in real quickly, but I'm going to do it right now. The kid's pulling. There's additional forces. So there's a force in the x direction right here, Fx, and there's a force in the y direction, Fy. Remember, he's pulling at an angle with 185 newtons. Yeah, he's going to have some x force and some y force. Okay, so that means that the 3 forces that we're interested in are parallel, frictional, and this Fx. Those are the only 3 forces that align up or down the ramp. Since the object is going up the ramp, I'm going to call up positive, I'm going to call down negative. That means that my Fx is going to be a positive value, a positive force, and I'm really going to subtract off these 2 forces. I'm gesturing with my pencil, but you can't really see. I'm really going to subtract off those 2 forces from my Fx. So it's going to be Fx minus the force of friction minus the parallel force, and whatever the result is of all those forces, that's going to be the ma of the object. Okay. So now it's just a matter of what are the formulas for Fx, Ff, and F parallel. Well, 2 of them are really easy. The Fx is super quick, and the F parallel is super quick. It's the frictional force that's going to be a bit of a pain in the backside to do. So let's just get to it. The Fx is, if we know from multiple videos before, that the Fx is the x component to this force, which is going to be 185 cos 25. That is right there. The force of friction, again, which is going to be a bit ugly, but let's just get it started. That's going to be mu sub k times the normal force, and the normal force is going to be the thing that's ugly. That's the part that's going to get messy here in a moment. And by messy, I mean like a little bit messy. The parallel force is nice and easy. It's just mg sine theta. And again, you know that from multiple notes. Okay. So let's get down to the nitty-gritty. The normal force. I'm going to zoom in a little bit on what's happening here. So this box, here's the ramp, and here's the box. The normal force is this force right here, and that has to support part of the weight. But notice that you are also pulling up on the object. So if you think about it logically, the ramp doesn't have to support the whole weight of the object because you're kind of supporting some of the weight of the object, right? You're lifting a little bit up on this ramp, so the ramp doesn't have to support the whole thing. So the normal force, instead of just being mg cos theta, so remember that the normal force is normally mg cos theta, right? If you remember your triangle. The normal force doesn't have to lift the Fy, right? Because you're lifting it. So that is going to be the adjustment that we make to the normal force right here. So when we plug this in, we're going to have 185 cos 25 minus 0.27, that's our mu. The normal force has this adjustment to it. It's going to be mg cos, now this is the cosine of the ramp, 12, minus, now the Fy is 185 sine 25. Remember, the 25 is the angle that you're pulling it at. Minus mg sine theta equals ma. So it looks like a big, huge mess, but it's not that bad. I mean, come on, it's not crazy bad. So now, if we're trying to solve for a, we're going to divide everything by m. But you know what? I'm gonna hold off on that for a second. Just to give myself a little bit of room, I'm gonna erase. You know what I'm not gonna do? I'm gonna use one of my tools. I'm gonna shift this over. I am going to shift this over here. Just for right now. I'll put it right there. Oops. So 185 cos 25. That's a calculator thing that you can just keep. That's a real number. Minus 0.27 times, now the mass was 35 times 9.8 times cosine 12. Again, these are all just numbers. There's no more variables. Now I took all those out. So far, everything here is calculatable. Oopsies, 35. I got all the way to the end. Of course, I make a mistake at the very, very end. So all this is equal to 35a. If you want to solve for a, you just divide everything by 35. So take this whole thing, divide by 35. And that, right here, is how you would get the acceleration. It's a long string of stuff, but they're just numbers. It's not hard to do. The one thing I want to point out here is that the physics was over. Once you did this, once you realize that these are the three forces, these two go in opposite directions, and the net total of those is ma. Once you did this step right here, the rest of it was an algebra question, right? The physics should be easy. Sometimes the math gets hard, and that's how physics class is that the physics is usually pretty straightforward, pretty obvious, pretty simple. It's the math that can get kind of teary and you cry and but the physics is easy, the math can be hard. Okay, that is how you solve 8. I don't know what the number is for that, but you guys should with your calculators out, and I'm going to post this video.